So we were discussing the chemical bonding, how the atoms are trying to be together to form a bond, and we have also discussed the ionic bonds. The ionic bond is formed when an electron is transferred from one atom to the other. That atom which loses the electron becomes positively charged, that is a cation, and that atom which gains the electron becomes negatively charged, which is anion. Now, we are going to discuss the tendency to form cations and anions. Look at the cations. If the size is larger, if the cation size is larger, then the ionization energy is lower. So the bigger atoms will have greater tendency to form cations. So when in the periodic table, when you move from left to right, that is along the period, ionization energy decreases. Sorry, when you move from left to right, the size decreases. Actually, what is mentioned here is size. Size decreases. When you move down the group, size increases. So when the size decreases, ionization energy increases because the distance between the nucleus and the outermost electron decreases. So when you move from left to right, the tendency to form cations goes on decreasing. And also when you move down the group, the tendency to form the cation is increasing. So look here, at the same time, anions, if smaller the size, then electron affinity is higher. When electron affinity is higher, it has a greater tendency to form anions. So when you move from left to right in a periodic table, the tendency increases. When you move down the group, the tendency decreases. See, fluorides. Fluorides of mercury and aluminium are ionic, but at the same time, chlorides of the mercury and aluminium are covalent. The reason is fluorine is at the top. So the size is small and the electron affinity is high. Hence, it is able to form ionic compound by gaining electrons. But when you move down, the chloride, its electron affinity is not that much high. So it tries to form covalent compound. So this is how the tendency to form cations and anions change in the periodic table. The next concept is formation of ions of higher charges. Actually, the formation of ions of higher charges is very difficult. The reason we have already seen, suppose if you take aluminium to form aluminium plus ion by losing one electron, this is called the first ionization energy. The first ionization energy for aluminium is a 577.4 kilojoule per mole. If you want to remove one more electron from the aluminium to form aluminium 2 plus, aluminium is already positively charged. So because of the effective nuclear charge, now the proton number is greater than the electron number. Therefore, the more number of protons will effectively attract the less number of electrons. So the removal of another electron becomes very difficult. So removal of an electron from a cation is comparatively difficult. So removing an electron from the Al plus to form Al2 plus. The second ionization energy is almost triple of the first one, 1833.0 kilojoule per mole. And further removing an electron from Al2 plus to form Al3 plus is much more difficult. It is 2703.5 kilojoule per mole. If you sum up all these things together, you are getting 5113.9 kilojoule per mole. So if you want to remove 3 electrons from the aluminium, and if you want to make an aluminium ionic compound, that is the ion with a higher charge, you will have to spend 5113.9 kilojoule per mole. But normally in chemical reactions, we are coming across energy exchanges of the order of 1500 kilojoule per mole. So with the 1500 kilojoule of available energy, you can never hope to supply 5113.9 kilojoule per mole to remove all the 3 electrons from the aluminium to form aluminium 3 plus ions. So group 3 and 4 elements, they are not forming ionic compounds, they form only covalent compounds. That is how aluminium chloride is a covalent compound, which is not an ionic compound. But when you put aluminium chloride in water, what you are getting is aluminium chloride hexahydrate. Actually, the structure of aluminium chloride hexahydrate is aluminium, 6 water molecules in the coordination sphere with a 3 plus charge for the coordination sphere, and the 3 chloride ions in the outer side of the coordination sphere. So this is the structure. If you closely watch this structure, it proves that aluminium is present in 3 plus oxidation state because water molecule is a neutral ligand. See, in the higher secondary itself, you might have studied what is a ligand, what is a central metal atom. So this aluminium is the central metal atom, and the water molecule is the ligand, and 6 ligands are connected to aluminium, and finally the overall charge of the coordination sphere is a 3 plus. So in order to compensate the 3 plus charge, Cl minus ions are present. 3 Cl minus ions are present in the outside the coordination sphere. How the aluminium is in the 3 plus oxidation state here? Because the previously we have explained the formation of aluminium 3 plus is chemically not possible because of the unavailability of such a great amount of energy. During chemical reactions, only 1500 kilojoule of energy is available, but 5113.9 kilojoule of energy is required to remove 3 electrons from the aluminium to form aluminium 3 plus. But in this particular reaction, you can done at home. You can take aluminium chloride anhydrous and add water. You can see the hydration is a highly exothermic process, very highly exothermic process. I think some of you might have seen the making up of calcium hydroxide using calcium oxide. How many of you have seen calcium hydroxide? You can raise up your hand and show me. How many of you have seen the conversion of a calcium oxide into calcium hydroxide? While whitewashing your house. In olden days, only at present we are not using this type of whitewashing. In olden days, we used to purchase the calcium oxide derived from the molluscous bodies. What are molluscous bodies? Molluscous means the living organisms with the shells, like sea oysters, crabs, snails. And these are all the living creatures with shells. Actually, these shells are rich in calcium carbonate. So what the people used to do, they collect all these shells and put in a kiln, and they will heat. In while heating, the carbon dioxide escapes and the calcium oxide is formed. Then the calcium oxide is bought. Then they will add water. You can see a vigorous exothermic reaction during the formation of the calcium hydroxide from calcium oxide. Normally, this particular process is not done in a metal container because even it can melt the metal away. It is always done in a clay pot so that it can withstand more temperature, high temperature. So it is this hydration process is a highly exothermic process. Actually, the calcium hydroxide which is used in the petal leaves for bida is also made like this, a calcium oxide plus water. So similarly, aluminum chloride, when it is added with water, this hydration process is highly exothermic, and this exothermic energy that is liberated during the hydration of aluminum chloride is sufficient enough to remove 3 electrons and to form aluminum 3 plus ions. And similarly, nitrogen 3 minus, phosphorus 3 minus are also not possible because of more energy is needed. So during the electro affinity process, I have already told you, electro affinity is the energy released by an atom when an electron is added, when an anion is formed from a neutral atom. The quantity of the energy released is called electron affinity. But when you like to add one more electron to an anion, it is already negatively charged. So the first electron affinity will be energy given by the system, but the second electron affinity will be the energy given to the system to make it accept one more electron. So N3 minus is further adding one more electron is practically not possible because more amount of energy has to be spent. So formation of ions of higher charges, when we discuss, the higher positively charged ions are not possible because of high ionization energy, and also higher negative charge energy is also not possible because of the high electron affinity or the high negative electron affinity, that is energy has to be supplied. So because of the energy considerations, the charges, the high charged cations and the high charged anions formation are not possible. Now, look at this. We are going to discuss the elements with variable valencies. The variable valencies means, so far we have seen elements of forming monovalent or divalent or trivalent cations or anions. And also we have already discussed that higher oxidation states are not possible. Now we are going to see the ions with variable oxidation states. So this is one of the peculiar properties of D block elements. We have seen alkali metals form only monovalent ions. Alkaline earth metals form only divalent ions. If you go to the right side of the periodic table, halogens will form a mononegative anions. And before that, if you take oxygen, sulfur, selenium, tellurium, they form a dinegative sulfide oxides or something like that. But if you take the transition metals, that is the D block metals, the outermost shell is not stable in the case of D block metals. And hence, the cations are also not quite stable. The outer shell loses one or more electrons, giving rise to metal ions of a higher valencies, which means that they can lose one after the other electrons. Say, for example, we can never say that the d orbital is a degenerate. P orbital is a degenerate. P orbital is a degenerate. But d orbitals are not a degenerate. They are with different energies. So what happens when little more energy is supplied, there is a possibility for the removal of one or more electrons. So that gives rise to metal ions of a higher valencies. So I repeat, the outermost shell is not stable. What is the outermost shell? The D shell. And hence the cations are also not quite stable. The outer shell loses one or more electrons, giving rise to metal ions of higher valencies. Say, for example, copper can form copper plus and copper 2 plus. Mercury can form plus and 2 plus. Gold can form plus and 3 plus. Iron can form 2 plus and 3 plus. Cobalt can form 2 plus and 3 plus. Tin can form 2 plus and 4 plus. So these are all the variable valencies commonly seen in the D block metals. Normally, when you name them, the ions with lower oxidation state are said as, and higher oxidation state are said as ic. Cu plus is cuprous. Cu2 plus is cupric. Next, Hg plus is mercurous. Hg2 plus is mercuric. Au plus is Rs. Au3 plus auric. Fe2 plus ferrous. Fe3 plus ferric. Similarly, cobalt 2 plus, cobalt 3 plus, stannous, stannic, something like this. Now look at this. Iron. Iron atomic number 26. Now you can see the electronic configuration like this. 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, and 4s2. Now look at this 3d6. 3d6 is actually a partially filled electronic configuration because a d orbital can accommodate 10 electrons to the maximum because it has 5 lobes. Each lobe can accommodate 2 electrons. So at the maximum of 10 electrons, it can be 10 electrons can be accommodated. So 5 is a half filled, 6 is partially filled. The 4s2